Okay, so here's where we were last time. We were we just barely started talking about this new theorem called Stokes' curl theorem. This is another one of these theorems that I like to call, depending on the context, sometimes I call them boundary theorems, because they all pertain to some sort of a domain and its boundary. some computation that's done on its boundary. Then there's also, I can sometimes call them accumulation theorems, because in all the theorems that I'm talking about here, what we are computing on the boundary, we view as actually accumulating over the interior. Even though we see it on the boundary, we compute it on the boundary, we see subsequently that it really is accumulating over the interior. And then finally, we write that as an integral and thus result in a sort of a density theorem. And so all of these quantities result in a new quantity, a locally defined quantity, that is the associated density, right? So change density, circulation density, flux density, these kinds of things. Okay. All right. So can we do such a thing in this new context of surfaces in R3? Now let me go through this next bit quickly, because we already talked about it. So as I just stated, we're going to be talking about surfaces in R3. I should say oriented surfaces in R3. So not just some set of points, but a set of points with an understanding that there is a well-defined positive direction through that surface, be it up or down or sideways or whatever. Okay. All right. On a given surface, you can talk about the boundary curve, and then the question of orientation comes up. And remember, our rule was that if you have a surface with an orientation, orientations on surfaces come in the form of normal vectors, right? Indicating, again, what's the positive direction of flux that you might calculate through such a surface. With an oriented surface, take your thumb, put it in the direction of that normal vector somewhere near the edge, and that defines a swirl, and that swirl defines a direction that we'll call the orientation on that boundary curve. Okay, so we talked about that a lot last time. Okay. What is the boundary quantity? This boundary quantity that I claim is going to accumulate over the interior, resulting in a new notion of density. What is this quantity? The quantity is circulation. By the way, just like Green's theorem. Right? So, in fact, we're going to see lots of analogies between this new theorem that we're developing now and Green's theorem. So, boundary circulation. If you give me some bounded surface, like something like this, right? Look at the boundary curve. You can ask how much is, given some vector field representing a flow of a fluid, how much is that fluid flowing around the boundary of that surface? Clearly that's computed on that boundary curve, right? What we're going to see is that it actually accumulates over the interior of the surface, even though we don't perceive it that way. Okay. All right. So, how do I know that it accumulates? Well, the argument is really, really similar to the argument for Green's theorem. In fact, I like to joke that you can take a piece of paper containing the argument for Green's theorem that it accumulates, and just take that physical piece of paper and do like this, right? And now you have a 3D model of such an argument for Stokes' theorem. It's the same idea. We're talking about circulation, right? So if I'm interested in the circulation around the outer boundary of this entire curve, this entire surface, right? I could ask, how does that relate to the circulation around the boundary of the left piece, and combined with the circulation around the boundary of the right piece? And notice that on that shared edge, C3, we cover that turf twice, right? Once in the positive direction, once in the negative direction. And by the way, if I had oriented this, let's say I had oriented C3 that way instead. Okay, well then instead of positive and negative, it'd be negative and positive, and it still cancels, right? So it doesn't really matter which way you orient it. So either way, on that curve, the shared boundary curve of two pieces of surface in the interior of the surface, you're going to be crossing that curve twice in opposite orientations, and they're going to cancel. Okay, so very, very similar to the argument for Green's theorem. And the result, again, is that these boundary circulations accumulate. Okay. How are we doing? Does anybody have any questions? Okay. By the way, I guess I kind of just dove right back into it, didn't I? Did everybody have a good break? And some nice time off? So for a lot of you, it may have been a week without thinking about math at all. That's a long time. So I hope everybody had a chance to crack the book a little bit, at least kind of remind yourself of the things that we're talking about here. So anyway, okay. Okay, so right, so a boundary circulation on a surface, just like it was in Green's theorem for a two-dimensional region, is a summation of boundary circulations over these interior pieces, just like it was in Green's theorem with interior pieces of area. Okay, since this expression is a constant, doesn't matter how you slice it, you can take a limit, because the limit of a constant is that same constant, so said differently, you can take the limit for free. Right? You can multiply and divide by surface area in a transparent attempt to turn this into a double integral. Right? It's starting to look a lot like a double integral at this point. Okay. And the question that we have to ask now is, well, I'm in the wrong color. Sorry. What is this density? If this expression that I have here is going to turn into a double integral, we have quantity equals double integral of what? Well, quantities are double integrals of densities. Right? So this is this new kind of density. By the way, you can explicitly see here, we're talking about circulation per unit area. Right? So we already know, whatever this ends up being, we'd like to call this circulation density. Okay. But what is it? How do I compute it? Is this a thing? So, understanding how to compute this is actually kind of a hard question. So I want to call your attention to a bit of a gap in my presentation so far. This is on purpose, by the way. So when we talked about the fundamental theorem of calculus and we talked about the fundamental theorem of line integrals, we came up with the corresponding idea of density. We talked about change density. Right? We talked about Green's theorem. We were computing circulation. So we talked about circulation density. When we were talking about Gauss's divergence theorem, we ended up talking about it was a computation of flux on the boundary. So we talked about flux density. But wait a minute, did we really talk about density in the context of the line integral theorem? We kind of didn't. Right? I talked about it with the fundamental theorem of calculus. I never really quite got to how do you think about the associated change density in the context of the fundamental theorem of line integrals. So there's this kind of gaping hole in this pattern I'm trying to develop as we go along. Right? Why didn't I fill in the blank of the pattern in that context? And the answer is it's a little different and it's weirder to talk about. And I like the idea of talking about it later, i.e. now, because the weirdness in talking about this, this density in the context of the fundamental theorem of line integrals, it's exactly the same kind of weirdness that we're going to find in Stokes' theorem. So here, let's go back to fundamental theorem of line integrals for a context that we already have some great intuition in, and let's try to understand the associated weirdness of the density that we end up with here, and that's going to be the perfect sort of stepping stone to understanding this new surface kind of density that we're talking about. Okay, so back to long ago. Okay, so change, right? Accumulates, take a limit for free. Change is the sum of a bunch of little changes, and then we end up with, looking at change per unit area, because of course I needed to make this an integral, and this then was a notion of a density, and we call this change density, right? Okay. Thing is, how do you compute that? Here's how you compute it. That's a flashback to chapter 13. I didn't write it exactly this way when we were developing the line integral theorem because didn't really want to go down this particular road. We wrote it as sort of combined with the ds, I'll say the delta s that we have here, and then wrote this as dx. Right? So at the time we wrote gradient f dot dx, which is perfectly fine, perfectly equivalent. I don't want to do it that way here, because here I want to think of it as a density. I want to think of this thing as something that I multiply by length to get quantity. Okay, all right, so we're leaving it as a density here, thus the slightly different form here. Okay, so is this thing that I have circled our change density? Well, yes, it is. This is the thing that you multiply by ds. Right, so you can see that right here. That times size gives you quantity, right? But in the integral that we end up with, when we write the fundamental thermal line integrals, we don't write it like that. We write it as gradient f dot dx, right? So is gradient f, the thing that's the integrand there, the vector field that is the integrand, gradient f, is gradient f the density? Well, no, it's not. Gradient f is, there it is, it's part of the formula for the change density, but it itself is not the change density. Yeah, everybody on board? This is a little awkward, right? But okay, so that thing there, gradient, it's not change density. There's a temptation to say that it's kind of less than change density. It doesn't give you all the information. I like to take a different point of view. I claim this kind of gives you more than change density. This tells you two things. This is what I like to call an oriented change density. The gradient is telling you, I mean, in a way it is telling you change per unit distance. Its magnitude is change per unit distance. Its magnitude is how steep is that mountain? How fast is this function changing? Just with an asterisk that, hey, that's how fast the function's changing in the maximum direction, in the sort of optimal direction, right? But then in addition to that, it is also telling you another thing. It's giving you a direction. It's telling you not only what is the change per unit distance, but it's telling you in which direction it's talking about. So thus I like to call it an oriented change density, because it's a vector. It's not just a magnitude telling you change per unit distance. It's a vector telling you change per unit distance in the optimal direction, and what is that direction. Okay. All right. So that's the idea of an oriented density. And how do you use that? Well, of course, I mean, look, the green circled formula is very clear. The density is that dot t. So you then have to say, well, what direction is your curve going? Right? If your curve is going through, like, how can I do better than that? If your curve is going, third time's the charm. Okay, there you go. If your curve is going through, at a particular point in that direction, given by a unit tangent vector t, that unit tangent vector you can combine with your oriented change density vector to get the actual change density. How we doing? Everybody on board? Okay. And by the way, it really matters, right? I mean, if you were to you can't just rewrite, the fundamental thermal line integrals. You can't just rewrite integral, gradient f dot dx. It would completely not make sense to say, you know what? Just look how fast is the function changing. Let's just look at the magnitude of the gradient. You can't just do that, right? That's completely not true. This dot product is very, very important. That's telling you how much of this sort of idealized change density are you actually getting in the direction that you're going. Yeah? Okay. All right. Okay. All right. So that kind of completes fills in a gap in our earlier discussion, and my opinion, sets the stage very nicely for where we were up here. We've got this thing here, this what I would like to call circulation density, because, well, that's circulation. I'm thinking of circulation as adding up over this entire surface. How much circulation per unit area is what I have to write down to be able to make sense of the integral. So circulation per unit area, I've got this circulation density thing I'd like to sort of go on with. What is it, and how do I get my hands on it? And it's going to be a lot like 2 seconds. It's going to be a lot like this. I'm not going to write down a single thing. I'm going to write down, there's kind of two things. There's the thing, but then there's also the dot product, and the orientation matters in a way very analogous to this, yes.
Why is the gradient of f dot like the t vector, even though like before we used df?
Yeah, so the point is that it's a question of whether you combine this into it or not, right? So if you take this thing, right, and now let's attach this ds or delta s here, right? And now let's look at this. Now that thing that I'm attaching, that I'm dotting with the gradient vector, t delta s, that is the dx vector, or the delta x vector, right? So it was just kind of a notational alternative. Let me write down the integrals in question. I don't know why I keep erasing that. So on the one hand, it's like here I'm writing down integral gradient f dot t ts, whereas in chapter 13, just because of the convenience of the situation, I was writing down this. And the point is that these are the same thing. Yeah. Okay. So, circulation, areas. Let's draw some pictures, try to get a feel for what this looks like. So here's the picture I want to focus on. And let's just think about, how does circulations happen around some little piece of area? What does that look like? Okay, well, here's a vector field. Right, and I'm trying to, by the way, this is a hard thing to draw, with a piece of paper, draw a vector field in 3 dimensions, but not just any old vector field, a vector field that's circulating. I mean, so forgive the imperfection in the art, but can everybody kind of see that there's supposed to be a fluid that's kind of flowing around like this? Yeah, okay, all right, good. Okay, all right, so let's ask for this vector field as I've drawn it here, and by the way, let's momentarily ignore this. We'll get to that later. Looking just at this part of the picture here, we've got a vector field representing a fluid flowing around like that, and let's look at this particular piece of surface. Right, and let's talk about the circulation, which of course means boundary circulation around this thing. Okay, now notice we have an orientation. Right, so there's an oriented little piece of surface, and let's see, right hand rule, so thumb, fingers, swirl, and we're going around now that way, around the boundary. Let's draw the vector field, this vector field. If I were to sort of extend, imagine, again, for the artistic purposes, you can't draw these things on top of each other. But now let's see how this rotating vector field, how would that manifest itself on the boundary here of this thing? Well, it's going to be kind of like that, right? And look at that. There's a lot of circulation around that boundary, right? So there's a temptation to say, hey, I can see circulation, I can see area, I could imagine writing down, a formula for circulation per unit area, just to work out the details in that picture, right? Okay, here's the problem. The problem is in this picture, right? Now don't look at that anymore. Notice it's the same vector field, still flowing around like this, right? We've still got a piece of area over here. Now, it's not oriented the same way, but it's the same size. It's as if I took this previous piece of area and just kind of tilted it like this. Well, now let's talk about circulation per unit area. Okay, well, here's the circulation again. Same vector field. right? As that would appear on this little piece of surface here. Well, gosh, I mean, the field lines are kind of like this on that side. I mean, keep in mind, the fluid is flowing around like this, but the surface is flat. So the fluid is coming up on this side, right? And then as it keeps flowing around, that fluid is then flowing down on the other side, which is going to be harder to draw. How much circulation do we see in that picture? Well, kind of none, right? I mean, the vector field isn't, the fluid is not flowing around this curve. It's not flowing along the curve. At any given point, let's say, I don't know, this one, at that point, the fluid's going that way, the curve is going that way. So there's no circulation happening there. Right, so you compare these two pictures, and let's address the idea again. Going back to where we were. This is the thing we're trying to compute. This is what we'd like to call circulation density. And let me make better color choices. This is what we would like to call circulation density, because circulation per unit area. It doesn't just depend on where you are. It depends on how you're oriented, just like it did here. Right, and let me erase this to reduce clutter. How much change density do you have at that particular point? You look at the gradient vector and it says, well, the function's changing that way. I'm not going that way. I'm going this other way. Right? How much change per unit distance is happening in the direction I'm going? It depends on the direction you're going. Depends on the orientation of that piece of curve. And likewise, circulation density depends on your orientation. Are you talking about a piece of area that's oriented like this? Or are you talking about a piece of area that's oriented like that? We have very different circulation densities, actual circulation densities, depending on much more than just where I am. It depends very critically on how is my piece of domain oriented. Is everybody on board? Everybody see the analogy between these two things? Okay. So, all right. So we would like to be able to look at, in some sense, the direction that the boundary curve is going around, and compare that to the direction that the fluid is circulating. And how do we get our hands on that? And that's a hard thing to get our hands on. It turns out a much easier thing to get our hands on is what is the normal orientation vector of the piece of surface. Notice that those are connected, right? However that boundary is circulating, that's uniquely determined, completely characterized by what direction is that normal vector pointing, right? And then, by analogy, we need a vector like that is pointing along the axis the fluid is going around, so that I can compare it to the direction of the normal vector that the boundary is kind of going around. Okay, so this is something we can actually get our hands on and compute, and here's how it plays out. This circulation density that we're interested in is computed by a formula like that. This vector that represents the axis that we're rotating around, and furthermore how much of this circulation is happening around that axis, is called curl. We denote it like that. Y'all recall from section 15.1, this sort of oddly convenient sort of reuse of the del operator, right? So this thing called curl. By the way, in parlance, very often people will say curl, but very often people will also say del cross. So del cross F, just because that's how, it's very often how you write it, and then you're just literally reading it as written. So be prepared. People talk about del cross F. They mean curl F. Okay. So circulation density comes from curl. Curl is your oriented circulation density. In the same way that gradient is your oriented change density. It's telling you more than just how much change per unit distance is happening. It's telling you the direction that that's actually happening in for your own comparison purposes. Likewise, curl here is telling you more than just how much of a little vortex do we have here. It's telling you more than just how much fluid rotation is there. It's telling you the axis also around which that fluid rotation is happening. All right, so the direction shows you the axis of the circulation. The magnitude tells you how much circulation is happening around that axis. Everybody on board? Okay. I think that I've thrown a lot of ideas at y'all here in these first 20 minutes of class. There's a lot to absorb. This is very geometrically taxing. Okay, so I want to encourage y'all. So, first day back from Thanksgiving, right? You still have tryptophan in your systems, right? So I want to encourage y'all, spend some time thinking about this comparison. I think this is a really useful comparison. Think about how gradient plays a role in the fundamental thermal line integrals as a tool for helping give you change density. It's not change density itself, it's a tool for helping you compute change density. Along those same lines, curl on itself is not change density, circulation density. It is a tool for computing circulation density. It's an oriented circulation density. Okay. All right. So with this having been done, now here's the formula that we're going to actually run with. This one right here. So this circulation density that we were trying to figure out what to do with, there's the formula, curl.n. By the way, I'm not going to prove in Math 212 that this formula is true, right? That's a bunch of details, and it's very interesting, but it's not something we have time for in this class. I think the far more important thing is to be able to understand what the result of the calculation represents. And the details of how to do that calculation are not for this course. Okay, so here's where we were. Right? So we had made the observation that circulation accumulates, and you can take a limit for free, and you can divide and multiply by delta S, and we say, hey, my gosh, this looks just like a surface integral, right? So we've got this surface integral, and the question was, what is this new integrand? What is that circulation density? Answer, curl.n, right? And so, you could, by the way, just completely stop and declare victory right here. There you go. Line integral around a boundary. Circulation around a boundary is a scalar surface integral of this integrand. I like to take it one next step. I think this is an important thing to do, in fact, to realize that you can kind of do the same thing we did back in the fundamental thermal line integrals. You can sort of realize that there's the way we have this partition, integrand differential, that's really an unnatural partition, because this is about the vector field. All of this is about the piece of surface. What you need to know about that little piece of S is not just how big is it, ds, but also how is it oriented, little n, right? And recall that we rewrite in ds as ds vector, right? So I think the aesthetics of this alternative version are much nicer. And given a vector field, what do you do to that vector field? Take the curl. There's your integrand. No, it's not a scalar surface integral. It's a flux integral. How it happens to work out. Okay. All right. And again, as always, we were computing circulation. The result is an integral, and thus we interpret the integrand as a kind of a density.
So, if we were trying to solve for like flux instead of circulation, would you use a surface area integral? Or would it like be the same? Like
it's very hard to use. You got a great question there, and I'm going to. You're just a little bit ahead of me. So I'm going to come back and answer that question, but I'm not quite ready to do it yet. It's a fantastic question, though, and I absolutely will answer it. Okay. So the first thing I want to do is kind of let's do an easy one, right? Let's get something under our belt, and then I'll come back and talk about that. Yeah. Okay. By the way, I always like to observe the fill in the blank when we get there. That we now have what had been a gap in this spot. We now have a theorem here, and the pattern holds. Right, let's reminder of the pattern. Fundamental theorem of line integral says if you take a gradient of a function and a boundary of a curve, then that difference is equal to that line integral. Gauss's divergence theorem says if you take the divergence of a vector field, you take the boundary surface of a solid, then that flux is equal to that triple integral. And, well, here we are again. If you have a vector field and you take the curl, if you have a surface, an oriented surface, and you take the boundary, the oriented boundary, then that line integral is equal to that flux. Same exact pattern. Okay. All right, so let's get one victory under our belts, and then I'll come back and talk about your question. The question says here, let's compute this line integral. Got a line integral given. The curve is parameterized, given to you. Right. The vector field is explicit. By the way, you could look at this question and think, hey, this is kind of a 15-2 question, and we've got not only an explicit vector field, but not only a curve, but the curve's been parameterized. This is primed, ready for plug and chug, right? Take that x, compute x prime, rewrite the integral as integral f dot x prime dt, do the pullback, etc. And you could do that. That would work. It wouldn't be pretty. Notice this is your x that you're going to have to square. Okay, well, yikes. This is your y that you will have to exponentiate. Even worse. All right, so this is not shaping up to be a convenient plug and chug problem. Okay. So then you might be thinking to yourself, oh, hey, it's a line integral. Here's an idea. Let's use the fundamental theorem of line integrals. How about that? Right? For which purpose? You need to find an anti-gradient, and it turns out you can't. There is no anti-gradient for this vector field, and I'll talk about why in just a quick moment. Okay. All right. So let's use Stokes' curl theorem. Stokes' curl theorem is another theorem that says, hey, you got a line integral? Great. We can compute it with this other alternative. And by the way, with all of these theorems, your ability to turn one question into a different question is not a promise that the new question you will turn it into is easier. Right? It might not be. It's nice. Well, it's something to try, though, and it's worth a shot. So let's try to use Stokes' curl theorem. Now, another reminder. We've talked about this for other theorems. Oh, sorry, I hit the wrong button. What did I just do there? Okay, here we go. I've talked about this for other theorems. If you want to use Gauss's divergence theorem to compute a flux, well, you'd better make sure that your surface is a boundary, because you need the what you might call anti-boundary as your domain for your triple integral. If your surface is not a boundary, there is no anti-boundary, there is no triple integral. The whole thing makes no sense at all. It's complete nonsense garbage. Right? So, likewise, here, if you would like to compute a line integral with Stokes' curl theorem, you'd better make sure that your curve is a boundary of a surface. There has to be a surface whose boundary is that curve, because that surface is the surface through which you do this new integral. if your curve isn't a boundary, there is no anti-boundary, there is no new integral. The whole thing crashes and burns, makes no sense at all. Just like in the Gauss context. Okay, so here we go. We got to go back to our question. And is this curve a boundary? Why, yes, it is. Right? Just got to make that recognition before you proceed. Otherwise, you're writing down nonsense. Okay. All right. So, so it is a boundary. It's a boundary of that surface. I've got my anti-boundary surface. That's going to be the domain for my new flux. Let's see here. Let me zoom in for visibility. My integrand is the curl, the given vector field. Right. So let's compute the curl. Excuse me. Here's the curl, and that's again just a calculation, right? Algebra. We have formulas for curl, discussed back in 15.1. By the way, make sure that you're clear on what the formula for curl is. Again, back in section 15.1, you can memorize the expanded form formula if you like. I encourage not doing that, because I feel like anything that has that many sort of terms in it that you memorize rote, you're going to forget, or you're going to conflate, or you're going to oops in some form or another, and then you make mistakes, right? So for whatever it's worth, in my life, I have never memorized that formula, right? I always just write del cross F and compute from that. So specifically, I always compute curls like this. Of course, the way you do a cross product, let's see, I need some space here. The way you compute a cross product is by this symbolic determinant. Let's use ISJs in case. And let's see, del F. All right, so the formula for cross product is this determinant. The del operator is there, and the vector field is there. Straight up. It's so easy to remember. Again, we had this long-standing formula for determinants. You already know that. So this is a freebie. Okay. All right. All right. So you do that for this vector field, by the way, and you get 002. Okay, so that's what we're going to compute the flux of. By the way, you got to love all those zeros. Right, that's really nice. By the way, furthermore, we need to know the normal vector in order to be able to compute this flux. There it is. Now, I suppose I could have parameterized the surface, but gosh, it's an easy surface. The unit normal vector is easy to write down. And so let's just write it down, and there it is, 001. And what we find out then, very quickly, is that this flux integral rewrites very nicely as just a scalar surface integral of a barnyard variety geometric figure, namely a disk, right? And so world's easiest integral, and there you go. Everybody on board? Yeah.
So this is just another way of computing a line integral?
It's kind of. So Stokes' theorem is a connection between two different things. So it could be that you want to compute a line integral, and you're going to instead compute a surface integral. Just now, for the record, it also could be, for whatever reason, that you're interested in a surface integral. That was his question, right? If you're interested in a surface integral, you can turn that back into a line integral. And sometimes that's a good thing to do. So that's the perfect segue for me to now answer your question. Let's talk about that. Can you go the other way with this? Now let's go back to the theorem here. Here's Stokes' theorem. Right, and we found ourselves looking at one of these. We had to compute the curl, no problem. The big question then was, is there an anti-boundary, what I like to call an anti-boundary? Right? Can you find a surface whose boundary is, it's better be a boundary of something, because otherwise the whole thing doesn't make any sense. Okay, all of that just flips if you want to go the other way. Okay. So, if you have a flux that you want to compute, well, you're going to take your surface and you're going to look at its boundary curve. Fine, no problem. Okay. But that vector field has to be a curl of something. You'd better be able to find what you might want to call anti-curl of that vector field. If you can't find the anti-curl, then you can't use the theorem. And that's really the sort of the deciding factor. And here's the bad news. Most of the time, you can't find anti-curls. Anti-gradients are pretty easy, right? We have a total formula, by the way. Let me, so, right? The analogies, again, super strong. Finding an anti-gradient is a process, right? You just kind of start taking some anti-partials and check a couple things, make sure that blah blah blah. But it works very often. Right? The analogous process over here is not so convenient, and it's not even really a process that I can just write down for you here in this context. So, roughly speaking, we don't do it. Yeah. Now, there are some rare circumstances when you can. One of them is if the flux that you have been asked to compute is somehow already explicitly written as flux of an explicitly given curl of an explicitly given vector field. If that's the case, then you already know your anti-curl, because the vector field was given as curl of a given. Does that make sense to everybody? So, other than a situation like this, yeah, we kind of really can't. Yeah.
So if that was the situation,
yeah,
you wanted to use Gauss's theorem to solve for the surface integral. Wouldn't it just be zero?
You got to slow down. I hear where you're going. I totally hear where you're going. You just almost I guess your hypothetical is sufficiently ambiguous that you may or may not have stepped on the landmine. But there is a big landmine here, and that is if you've been asked to compute a flux, right? Okay, well, you say, okay, well, I'd like to compute this flux. Can't I just do this? Well, it depends. You have to know that surface has to be a boundary of some solid. And if it's not the boundary of a solid, then Gauss's theorem does not apply. So you see what I'm saying? So even if the divergence is zero, so what? Right? The divergence can be zero all at once, but if your surface is not a boundary, then there is no accumulation over the interior because there is no interior. Right? So let's look at flux through this surface here. Right? Suppose the divergence is zero. All right. Right? So let's take this flux and let's view, is this flux an accumulation over some solid? No, what's solid? There is no solid. You see what I'm saying? Yeah. No, it's very tempting. I cannot tell you how many students, and again, I'm not accusing you. Your question was sufficiently it's perfectly fine, right? But every year, so I'm kind of sensitive to this question, right? Because every year I get, I don't know, 3 or 4 students who will make a mistake of the sort of, hey, it's a flux and the divergence is zero, and they will just write divergence is zero, flux equals zero, pen down, right? That's it, and it's not a valid argument. It makes no sense. So yeah.
We have to explicitly say that it's like there is a boundary of a solid. Or would that be?
It depends on how it depends on the context. So if you've been given an explicit surface and if you're going to write it, as a triple integral, then you're going to have to say what that solid is somewhere, right? In other words, giving it a name doesn't doesn't make it a thing, right? So, I mean, if it's sufficiently, like if I've asked you about a sphere, and if you say, okay, well, flux equals triple integral, and you call it B, right? Yeah, okay, I understand. It's clear that you're talking about the ball, right? But if it's, I don't know, I think it never hurts to be clear, right? So you might say, draw a picture and then put an arrow and say, this ball is the solid. Yeah. Okay. All right. Okay. Oh yeah. Mm-hmm.
Where did you get the unit normal vector for this surface?
Oh, great question. Okay, so he asked, where did I get the unit normal vector? Here's the surface, right? The curve was parameterized like that. Note that parameterization implies an orientation, right? So the curve that I'm given is oriented that way. Does that make sense? Okay. So when we're sort of reverse engineering the boundary operator, we also kind of have to reverse engineer the orientation. So yeah, sure, this disk is the surface whose boundary is that curve, right? But what orientation would we put on this disk? Why that one? Why not that one? Right? And it's just about the thumb game. Right? So you got to play the game twice, right? So first attempt, maybe you put your thumb down the thing. Okay, well, let's consider the possibility the normal vector might be down. Look at how your fingers go, and they're going the wrong way. Oh, okay, well, I guess I guessed wrong. So it's not the down one. And then second attempt, thumb in the direction of the upward option, right? Look at your fingers. It's swirling the correct direction, and so correct. Yeah.
What about the actual coordinates? Like if the surface is just like tilted?
Oh yeah, well, so it's different every time. I mean, here I took advantage of the fact that the curve, being as it is in the XY plane, I can say, let's look at the disk that's in the XY plane, and once I know it's in the XY plane, it's horizontal. Normal vector's got to be straight vertical. This is the unit normal vector, so it's pretty clear, right? But you're quite right. I mean, if you have a different surface, it's not, this particular process might not be the convenient way to do it. It might be better in such a case to, instead of doing this, it might be better to actually compute this flux by parametrizing the surface. Yeah, absolutely. Okay. All right, I got a couple minutes left. I want to talk about an idea that we've already talked about a lot, actually. So I want to flash you back to when we were talking about Green's theorem. Right. So this page of notes on the right is from 15.4. This is a long time ago. Right. So Green's theorem. We had this set up where, you look at a couple of points, and those 2 points, let's consider two different curves that have the same starting point, same ending point. Oh, check it out. They sort of could be thought of as two different parts of the boundary of this region. And then we looked at Green's theorem, and we made a couple of different arguments based off of Green's theorem to show how when Green's operator is 0, you have a gradient, and furthermore, if you have a gradient, then Green's operator is 0. It all comes out of Green's theorem as applied to that picture. So again, take that picture, do like this. Now you have a picture for Stokes' theorem. So here it is. Let's think about Let's think about a surface. Now this is a surface in space, so it's, bumpy and wiggly. Right? And, well, I could think about points on either side and curves that start and end at those same 2 points. And look how the picture is a ripoff of the one over there. Morally the same. Right? Here now, we're not going to write down Green's theorem, because there is no Green's theorem in the three-dimensional context. It's Stokes' theorem. And the exact same arguments go through. Well, I say exact. They're obviously a little different. The totally analogous rip-off arguments go through. And for the record, as I was writing these notes, I deliberately copied, as the format as much as I possibly could to emphasize the strength of this analogy here. It's extremely strong analogy. So in the same way that you might say over here that, what's really going on in this argument is Green's operator is talking about circulation density. If circulation density is 0, then circulation is 0. And if circulation is 0, then these two line integrals are equal. That's path independence. Okay, well, same deal on the other page over here. Same exact deal. Curl is telling you about circulation density. It's oriented, but no, but still, if the circulation density is the 0 vector, that means there is no circulation. No circulation like that. That means that these two line integrals are equal, and that means path independence. Again, it's really very much the same idea. Okay. All right, and sadly I'm out of time, and so, we keep getting further behind schedule. Okay, we'll catch up. We'll make it. This happens every year. That's fine. No problem. Okay, see y'all later. Have a good one. Oh, a quick reminder. I do